All right, good morning, everybody. Hopefully this is all coming across very nicely for everyone. The session today is choosing your clustered index. See if we can get this to scroll forward. There we go. My name is Jason Strait. I'm a database architect here with Pragmatic Works, and I've been working with this for a while. And I actually know something on this screen that's already incorrect. I thought I'd fix this last night, so I'm just going to fix this really quick just so that we have the right link on the screen so that the people that watch it in the recording do actually see the right screen. It should say, for all the resources for what we're going over here today, if you want to go and get anything on them afterwards, just go to jasonstrait.com/go/indexing, and this deck, along with some other resources, will be available. As was already mentioned, this recording will be available by tomorrow, and I've done quite a bit with indexing. I do like talking about it, and that's why we're here today. So Pragmatic Works is sponsoring this presentation here today, along with all the training on the T's. I'm sure you've heard enough already today, and you're already familiar with Pragmatic Works, so I'm not going to dig into this and talk too much about us, but instead I'm going to talk about how, when it comes to our databases, one of the biggest things that we need to do is navigate to data and get through the data and get what's in the database back out of it. It's our primary responsibility after we've got that data stored. And the problem is that in some cases there is a challenge in getting to that data because we don't have it stored in a way that makes it easier just to get right in there. And we need to be able to get into it and not make it this black hole that's storing all of our data, and find a way to get it out fast. And getting it out fast is what everybody wants to do. It's the end game of getting to our data. You know, we want to make some great analytics on it. We need to solve some OLTP issue, or we need just to make sure that our database is getting the data out so we can ship product out to our customers. It's all driving this performance that we have. And when we're talking about clustered indexes, this is the way that we want people to, or not that we want people to get to, but the way that people are going to go to our data, and it's the shortcut to that data. You want to make sure that whatever your clustered index is the way that most people, when they're querying the data, are going to that data, and you want to make sure it's honed in on that. And that's what we're going to be talking about. We don't want to use alternative routes that go to the data. That's for our non-clustered indexes, and so we're going to focus on that shortcut and why it's important to have the clustered index and some of the patterns that you can use for getting to our clustered indexes. And those are some of those options that we're going to look at today. And that's kind of an overview of what we're going to be looking at. So we're going to first go into, after this introduction, we'll go into some information on clustered indexes and heaps. We're going to talk about the qualities of a good clustered index, and then we're going to look at some clustering index patterns before we wrap up. And these patterns are just different ways that you can implement clustered indexing, what's good and bad about them, and what effect that they have on execution plans, and why you choose one over the other. And so as far as our goals go for today, we're going to define basically clustered indexes, explain those rules like I already mentioned, and then we'll do some demos. And hopefully this is what you're going to get out of it, is these three items. So let's get rolling right into this and get into looking at clustered indexes and comparing them to heaps and just the clustered index itself. Now I mentioned that we're focusing on choosing a clustered index, but there is an alternative to choosing it, and that's not choosing it. And that's where the heap structure comes out. By default, if you just create a table and you don't put any physical structure onto how the data is going to be stored, SQL Server is going to store it in what's called a heap structure. The heap structure it's unordered. The first record that you put into it is going to be the first record that's in there. And it doesn't matter anything about numbers or alphabetation of the data. I think I just made up a word. It's basically the data just goes in there. There's no way to say where one row is versus another row besides just going in and scanning across everything to find out where that one row is. And so with heap structures, things get very what I call scan happy. If you don't have auxiliary indexes that are assisting the heap structure to find rows, it's going to just scan the entire table every single time. And generally that works okay for very small, tiny tables, but not for larger tables. And so there's quite a few compelling reasons not to use heaps. And just to kind of reiterate how this is unsorted, if we've got a number of pages, and let's just pretend for a moment that all of our rows map to a single page. Every row is 8K, and so it's going to fit on a single page. And if we get all of these rows, the way in which SQL Server is going to store these is, if you've got Alan and Ryan and Sarah, Madison, Joey and Jane, Zoe and Jane all coming in, with a heap structure, the way in which SQL Server is going to organize these as they come in is storing them as they come in. And so what SQL Server will do is it'll allocate an index allocation map page in the first row that gets added in, and in this case we'll say it's Madison. Madison will be the first one placed within the table. And then it'll go to Ryan, and then Zoe if they were inserted in that order. And if that allocation map is filled out, maybe another allocation map may be allocated out. And then Sarah and Alan and Jane will be allocated out to it. And that's basically how heaps are structured within SQL Server. And so if you go and you ask for Zoe, SQL Server has no information based on heap to know where Zoe is going to be. And so in order to check for Zoe, every single page has to be checked to see if the row for Zoe is stored on that page. And hopefully in the way that I've described it, you get that understanding that there is no way to know exactly where a page is going to be if there is only one page or one row that has that information. And so that's kind of the downside to the heap. Now, the alternative is to choose a clustered index. And the clustered index is basically, it's a mechanism for storing the data within SQL Server. It enforces an order onto your data in such a way that certain rows will appear in certain orders, and you can then pull through SQL Server to figure out exactly where rows are. And it's often that you want to store your rows based upon whatever value is or information that you use to primarily pull the data out of that table. If you're pulling out data based upon name, then you might actually, if name is like the most frequent way, you may actually cluster on name. If you've got a sales table and you're pulling out by sales orders, well, then sales order ID makes sense for your clustered index. It's generally geared to pulling out by what's the most frequently leveraged item. And so in this case, if we've got, in this case, our Zoe and Ryan and Sarah pages, and if that is what we're keying off of, those pages would actually be stored physically within SQL Server based upon those values. Now, I'm oversimplifying things here because SQL Server logically stores these in physical order, but it won't always, logically stores them in order, but it won't always physically. You can have rows that appear within a page that are not stored in order, but from a logical perspective, when SQL Server is accessing the index allocation map and then the root page for the index, and then going down and grabbing the Al and the Jane, it can be that physically they may be a little bit out of order, but logically SQL Server knows the order in which records are stored and can go directly to the Sarah page. It doesn't have to check all the other pages to verify where that information is stored. It can go just directly to where that's at. And that's that value of the clustered indexes. SQL Server knows where pages are. And so let me show you how these work out. So let me bring up the demos here. And what I'm going to do is I'm just going to create this table. It's from the AdventureWorks database. And it's just a sales order table with all the non-clustered indexes that are already on the sales order table. But just put it into a table that's basically a heap. So without the clustered index that comes with it by default, so we'll get that created. And as I mentioned already, heaps are a bit scan happy, and so there isn't anything that says exactly where the sales order ID rows are stored. And so if we go and take a look and query against our heap, what we're going to find initially is, take a look at that execution plan. In that execution plan, it had to use an alternative index or a non-clustered index, even though I'm calling it the primary key. And it is the primary key, but it's not clustered. And so this table it's got a heap structure. And so it's going to go to the non-clustered index to find out where that sales order row is located, and then it has to do a row lookup. And this row lookup then and pushes it through. Now, if we go and we do against the sales order header that has the clustered index, we can see that it instead can just use the clustered index to go directly to, and in this case the clustered index is the primary key, and it can go directly to that data. And that's part of the initial value in doing it. Now, as I've talked to people, a lot of people will say, well, with little tables I don't necessarily need to use clustered indexes, say like when I'm doing temporary tables. And that can be true in a lot of cases. And let me just create a couple temporary tables here. And it's the exact same temporary table, and in this temporary table I'm just putting in some sales order information. And I'm just going to do a join between the temporary table and a detailed table. And in some cases, when you're working with small amounts of data, you won't get a very big difference between a heap and a clustered index. In this case, we'll just take a look at that. And we can take a look at the execution plans between the two of these. And we'll notice that for both of these, we're going to end up with a scan. And so in some cases, when you do get scans against both a clustered index and a heap, it doesn't necessarily make a big difference. We get the scan in both of those, and then we get the seek across the non-clustered index. So it's not, or the clustered index is on another table. So it doesn't always make a big difference. But sometimes even on small tables, though, this will make a big difference. And I'll create those same temporary tables, because sometimes when you're working with different constructs within T-SQL, you'll generate issues where heaps matter and you want to choose a clustered index. Let me just show you guys this example. Bring up the actual execution plan. Oops. The actual execution plan, we'll run that. So we get the exact same outputs. If we take a look at the plans, we can see that because it's doing the exists, it's doing a scan against that clustered index, but because the exists is trying to optimize so that it checks once and it doesn't check twice for the same values, the temporary table that's using a heap is resulting in a sort after the scan, which is then driving up the cost. Now the cost difference isn't that much, but there isn't a lot of rows. And as you get more and more rows that you have to work with in these cases, there will be cases where even on a temporary table, having a heap that's clustered having a temporary table that's clustered will provide additional benefit over a heap. In general, though, when you're working with tables and you have to choose whether or not you're going to have a clustered index or a heap, I'm going to let you know that generally you're going to almost always want to have a clustered index on your tables. Unless you can prove that a heap is going to improve performance, you want to cluster all of your tables and all of the indexes. When I do assessments with clients, this is one of the things that I look for, because I can almost always, unless they can show me that there's a use case where the heap is performing better than the clustered index, you want to choose to have a clustered index on your tables. So once we've figured out that we want to have a clustered index, we need to figure out where the clustered index needs to be on these tables. And before we start that, let's talk about some qualities that make clustered indexes good. Some things that make it a better clustered index over other choices. And this basically falls down to 4 different characteristics. You want clustered index values to be static, and the reason why you want it, well, I'll go over each one of them first, and then we'll go through some of the details. You want it to be static. You want the value to be narrow. You want it to be unique, and if possible, you want it to be ever increasing. And when we're talking about it, that you want it to be static, the reason why you want it to be static is if your clustered index value changes because it affects the sort. If the value isn't static, you're going to be moving that row every time you update that value, and by moving that row, you're going to impact the fragmentation of the index and cause a lot of different things to move around. If you move the location of the row for the clustered index, you then have to update all of the non-clustered indexes to say where that row is now stored. And so that's kind of an important quality of clustered indexes. Let me get Skype turned off here because I turned Skype on right before we started here today so that I could communicate with Rachel. So the next characteristic is narrow. You want your cluster indexes to be as narrow as possible. And the reason why you want it to be narrow is, as I mentioned a little bit already, that clustered index value actually gets placed within every single row within non-clustered indexes. And the wider that value is, the more space it's going to take up in your non-clustered indexes. So not only does it take up space within the clustered index itself, but it does have an impact on non-clustered indexes. And if you have, an extra gig or two because of your size choices with your non-clustered with your clustered index keys, it's going to have a drastic impact on those non-clustered indexes. And here's the thing to think about. By default, and what most people will end up using is an int when they're doing their clustered index. This is the value that the data type that many of us will use for our non-clustered index. And so when you're talking about having 10,000 or 100,000 or 1 million rows, you're only talking about three, almost 4 gigs worth of data that's just that clustered index. It's not a lot of data. If you go out, though, to a 32-character value, and in this case, this could be, if you're leveraging a unique identifier, or you have multiple rows, multiple columns within the cluster index, you're going to be storing a lot more data. And it's not a lot more when you consider maybe 1 million rows, but we're starting to see databases where 10 million or 100 million rows are a real possibility. And I've started working with some of the data warehousing I've been doing with tables that have 1 billion rows. And when you start looking at the larger data types, if you're looking at a 32-character data type, or 32-byte data type, you're talking about an extra 30 gigabytes of space. Well, not an extra 30, but an extra 27 or 26 gigabytes of space in your non-clustered index that you probably don't need. Because when you're looking at just using an int has a lot of rows. Now, you might end up using, if you've got multiple billions of rows, you might end up using a big int. In that case, you can go up to, I think if you add in, say, 1 million or so rows per minute, you've got a few thousand years worth of rows. So, a big int can cover a huge span of data. The difference, though, between the big int at 1 billion rows and the 32-byte data type at 1 billion rows is quite significant. And the thing to think about is that that significant difference is a significant difference to not only your clustered index, but to all of the non-clustered indexes that are on that table as well. And so that's the thing that you have to pay attention to. And that's why keeping it narrow is very important. It's because of that additional impact to all of your clustered indexes and your non-clustered index that you have to pay attention to. Now, unique is also important. And the reason why unique is important is because of the uniqueifier. If you have a non-unique clustered index, SQL Server needs to make it unique. And it'll make it unique under the covers by adding a uniqueifier value. So the first time that you add, let's say we're making name our clustered index. And if the first row comes in that's JSON, then it'll just store JSON. The next time a row comes in, if it also has JSON as the key value for the cluster index, it's going to then add on to JSON and a uniqueifier value, and it's an int value. It's an int data type, and so the unique row for that second one will be JSON, and then that one value that'll be sitting out there. And the reason why it's important to keep it unique is those uniqueifier values add up as well. And so when you add on that uniqueifier, when you have 10,000 or a million rows, it's an extra 7, that value, it's an extra 7 megs of data that gets added on. And over time, as you have more and more rows and your base size is increasing, you're going to get a larger and larger unique value for your row. And it's the same problem with keeping it narrow, but you're adding on this extra 4 bytes that you didn't have to have there if you just had a unique value to start with. Now the fourth is ever increasing, and the reason why you want to keep things ever increasing is when you're adding in rows, and so you say you're adding in 1, 2, 3, 4, 5, 6, and these are the rows that you're adding in, and supposing that they get their own page, by doing it in ever increasing data type or data value, you're going to be putting in the rows in the order in which SQL Server wants them to be, because clustered indexes are sorted based upon the key values. But if you put them in the order of 1, 3, 5, 6, 2, 4, SQL Server can't store them in that way logically. SQL Server is going to then need to reorder the logical pages, and the rows will then be in order, but it has to do things like page splits and add fragmentation into the index, your clustered index, in order to get the pages in place. And that presents a number of issues, especially when it comes to trying to get and keep things running quickly, because the time that you take to split a page is time that you're taking away from processing other operations. And the fragmentation that you add in is adding in additional pages into your clustered index, which then takes up more memory and takes memory away from other things that you can be doing. And so keeping them in order can be important, is important in that regards. And those are the core rules that go into choosing a clustered index, but they're not unbreakable rules. There will be times where you might break 1 or 2 of the rules because it makes sense for your database. And that's where we're going to get into talking about the patterns. There's a number of patterns that you can apply to choosing a clustered index that will make sense for your environment. And if it makes sense for your environment, it is the way to go. Just because something is a best practice doesn't mean that you absolutely have to do it. It just means that in a majority of cases, it works. And it's a good place to start from before you settle on what you need to be doing. And so as I've been looking at clustered indexes, I did identify that there are basically 5 ways in which you might choose a different clustered index. Now, these are kind of put into order of preference. And so the first one is an identity column, then there's a surrogate key, a foreign key, multi-column, and the last one is global unique identifier. I really shy away from the last one, and we'll talk a little bit about that towards the end. But let's start off by just looking at the identity column. when you're doing the identity column, and this is where you're going to want to start when you're building up clustered indexes for your tables. And basically, what you're working on, what you end up doing is you add in either an int or a big int onto your table. You're going to use the identity property or end up using a sequence to assign the identity values. And as rows are added in, you're just adding in a new distinct value for every row, and that's going forward, and that's adding in different values. And this is pretty much, when you're looking at the 4 properties, the one that most closely aligns. It's going to be static, it's going to be narrow, it's going to be unique, and they'll be ever increasing. And so as rows are added in, this is the pattern that goes in. And this is where you're going to start in pretty much every case. Now let's take a look at that just so you can understand exactly what that pattern looks like. So I'm going to create a table here real quick. And this table is going to just have some indexes, some fruit. And it appears that I already created that table. So let me just drop it real quick, just to make sure that that's exactly what this demo is looking for. So we'll get that created. We're going to add in some apples, we're going to add in some bananas, and we're going to add in some grapes. And the reason in which you might want to do this is because if you take a look at the fruit that I'm adding in here, there's actually 2 apples. And so apple's not a unique value. There's a red apple and there's a green apple. So there's 2 different attributes that define what an apple is. And so the apple isn't what can make it unique. And so the type of fruit won't make it unique. You could look at doing color as being unique, but when we're talking about storing fruit, color is not a really good value to make unique. And plus the fact that there are actually 2 types of fruit that are green. And so there isn't that really unique value, and that might be what drives you into first starting off with just creating a fruit ID that just identifies all of your fruit. And as that gets built out, what you end up getting is you have your apples, you've got your colors, and you can have that non-uniqueness within the colors and the fruit names, and you have another value which has no relation to the fruit name, has no relation to the color. You're not going to have to update it for any reason because it's almost a meaningless value, but the fact that it's meaningless adds a lot of value because you can use it to uniquely identify any single row of data. And so when you want to go and query against it, you know that you want to go and pull out apples that are green, and so you can do a filter on apples that are green, you get that fruit ID, and then you can use that to look up things in other tables. And this is basically where you're going to want to start. You could also use the sequence value that's available in SQL Server 2012, but in the interest of time, we're not going to dig into that. And so this is that first pattern. This is the way that most databases, most tables, and most people start off when they're choosing how to decide on a clustered index. Now the second is going to be a surrogate key. Sometimes there is a value that is unique, that is unchanging, that can be used. And this is going to be things like an employee ID. If there's an alphanumeric employee ID that gets assigned, if there is a social security ID that gets assigned, maybe there's a birth date that gets assigned. Now, these are values that you can use for specifying the keys of a table. Now, the trouble with some of these is that in many cases, surrogate keys, while they appear to be a really good fit, they're generally static. They're not going to change. Oftentimes, they're going to be narrow, and it depends upon what the value is. If it's a date, you're talking about 8 bytes. If it's a social security number, it's going to be a string, and it might be 12 characters that you're storing. So it's generally narrow. It should be unique because, for instance, social security number should be unique. Of course, if you have fraud in your database, it won't be unique, so it's not always unique. It does really violate that rule of ever increasing. And oftentimes, if you do think about surrogate keys, and we look at the examples that I actually have up here, employee ID, or social security number. Those, depending upon business rules, if your company gets purchased, those values may change over time. They're probably, even though they seem like really good surrogate keys, they may actually, over the long term, in the long look on your database, be a really bad value for doing surrogate keys. Now, I have on their birth date. That's kind of a chuckle because birth date isn't a really good surrogate key, but if you have a table that's full of dates, why add in an auxiliary value to reference a date when January 1st, 2012 will always be January 1st, 2012, and that can make a really good surrogate key. So let's just take a look at that, just so you guys can see that in action. And so we're just going to create a table here. And into this table, I'm just going to put some states. Now, being somebody that's from the United States, I can add in Minnesota, I could add in Florida, I could add in Wisconsin, New Hampshire. We can have all those added in, so we've got our states table, and they're going to be then sorted based upon, within the clustered index, based upon the values of the state abbreviation. Now, I haven't filled this out with all the different state abbreviations that are out there, but this is also another case of one of those ones where it seems like state is a good one to use, but if you start thinking long-term, you start thinking internationally, state abbreviations are actually not a really good fit. So pretty much every time that you have a surrogate key that you want to make your clustered index, you may actually want to rethink that, because in the long term, most surrogate keys, you're going to want to go back to the identity. But there will be some cases, like dates, where it does make sense. And that's surrogate keys. And one thing I haven't mentioned yet, if you do have questions, please put the questions into the Q&A slot. I will answer as many as I can towards the end. We do have a hard cutoff at 12 o'clock Eastern, but any of them that I don't answer, I'll end up answering through a blog post afterwards. Now, the third pattern that's out there is what I call the foreign key relationship pattern. And this is where you have one-to-many relationships. And in general, the access path to whatever's in the foreign key relationship, you're going to go through the parent versus the child fields. And what I mean by this is if you have an order header and you've got details underneath it within a details table, you're often not going to use the details ID to get to your data. You're going to go through the order header, because often you don't care about the detail ID. The detail ID is just a value to make rows unique, and so that you can find out in this order, there was paper towels ordered and there was toilet paper ordered, but what identifies those individual rows doesn't really matter. What matters is that when I go and I ask for that order that I made, that I get both of those back, and I get them back as frequently as quickly as possible. The nice thing about the foreign key pattern is that it is static in general, unless you've got where the foreign key relationship is changing. Now, in orders, you typically wouldn't have that unless you're combining different orders. And so if you're combining orders, you may have orders that shift around and rows within the details that shift to match where the new header is. It's generally unique. I mean, it's generally narrow because you're typically combining two integer values together, the foreign key value from the primary key value from the parent and the primary key value from the child. It is unique because you do have the unique value that you're adding on there. And it is kind of ever increasing. And the reason why I say kind of is that as your orders come in, your orders are going to have their ever increasing value. And then that's going to trickle down to your child table. The case where this becomes not ever increasing is if you have an order that was placed and then later on you come back and you add more to that order, those rows will need to be placed within the middle of the index. But let me show you how this works and how this can be really powerful with your system when you're dealing with foreign key relationships. And so what I'm going to do is I'm going to create two tables here. The first table is going to have a header, and then it's going to have some detail information. And in this detail information, in this first one, I'm tagging it with ICP, which is standing for Identity Column Pattern. And so I've got an identity column, and I'm putting the clustered index on that single identity column. And then creating a non-clustered index on header ID. And so header ID and detail ID, that's our primary, unique values, and header ID is what ties in the header to the child. I'm going to create a second table for details that has this foreign key pattern that I'm talking about right now. This foreign key pattern then is going to take, instead of the detail ID as the clustered index, it's going to take the header ID as the leading value for the clustered index, and then have the detail ID as part of that. And so that within the detail table, it's first being sorted by header ID, and so it's keeping all of the items for one header or one set of rows together with each other. And so I'll get both of these created. And I thought I would have that problem because I did create these tables last night. I'm not actually going to drop them, but I will just say this is the script that I use to take a look at them, to pull them together. So what I want to show you is what happens when we're pulling records out. So we're going to pull some records out here. We're going to start with just pulling out a single row. We're going to pull out one header and all the detail records. And so if we do that, and we're just pulling out a single record, we're going to see that there's not really big difference in performance. So we've got one row, one header, and we got one detailed row. And those come back together. If we take a look at the reads, we're going to see that there is only a slight difference in performance. When we're looking at logical reads for the identity column pattern, we do have a bit more reads against the detail. So there's a slight performance difference there. And then it's a bit minimal when you're looking at the foreign key pattern. And the reason why you get that difference is when we take a look at the execution plan, there's a difference here in the execution plan. And let me just expand this a little bit so we can see the whole thing on the screen. There we go. Almost have it, the whole thing here. And so while it didn't look like there's a big difference from the output, and there wasn't a big difference when it came to the reads, there is a difference when it comes to the execution plan. And what's happening is that because the identity column pattern has to look each row up, it's got to do a bit more extra work because the header rows, the ones that match that header ID, aren't grouped together. And so what SQL Server is going to do is it's going to go and find the header rows that it wants. It's going to come down in and look for the non-clustered index rows that match that header row, and then it's going to go back to the clustered index on the detail row to pull out the additional information that it needs before then it goes back up and returns the results. Where if you store your header rows in the detail table together, instead of having to do the additional nested lookup, the index seek, and then the key lookup, it can just do a single cluster index seek, pull the rows together, and then pull everything together in a nested loop and pull it back out. And this is a pattern that when I've seen detail tables and header tables used in conjunction like this, where you do want to do the filtering on that specific value, that this has a lot of power. And as an example of where this actually starts having a big effect on performance is let's take a look at if you're actually pulling up multiple header rows. In this case, I'm going to go against the same tables, the exact same detail tables. Instead, I'm going to pull out not just one record, but pull out a range of records. So let's turn on the execution plans. We'll run both of these. We will get the same results from both. Both of them we're getting 79 records. We're getting multiple rows that are coming back for each. And if we take a look at the I/O for each, we're seeing that there is a significant increase in I/O between the two. And the index pattern, the identity pattern, is performing a lot slower than the foreign key pattern. And the reason for this is if we take a look at the execution plan, because the detail records aren't stored together, they're not stored with the header ID, we're more quickly falling into a place where the execution plan tips and we go to a clustered index scan across the detail records. And if you think about your systems where you have these parent-child relationships, typically these detail tables have a magnitude or more records than the header rows do. And the place where you don't want to see an index scan result is across that detail table. And in this case, because we wanted to bring back a number of rows, we got to the point where doing that key lookup was going to cause a higher I/O performance impact. SQL Server had to go to the clustered index scan, where by using that pattern, we can do the clustered index seek and then just do a merge join to pull those records together. And this here's the one clustered index pattern that I really like to make sure that people know about, because this can have a big difference in a lot of systems. And it's one that people, if you're defaulting into the index, the identity pattern, which is the one that I do recommend people default into, if you don't recognize that this pattern is happening, that you have these kind of relationships, you can see a lot of performance problems. So that's the foreign key pattern, and hopefully after we're done here today, you'll take a look at your own systems and look to see if you have this pattern that you unknowingly are supporting. Now the next one is the multi-column. This is really similar to the foreign key pattern problem, or pattern, but it exists between many-to-many relationships. And the reason why you want to pay attention to this a little bit differently than you do for the foreign key patterns is that it's highly dependent on selectivity. The more selective you have the columns set up, the more likely you are to improve performance. And so let me first talk a little bit about this, is that it's not necessarily going to be static. In some cases it will be, but if you have a situation where you have a person and the person can have multiple job roles, and there's a list of job roles that they can possibly have, they may shift around between job roles. It's going to be kind of narrow because you're probably talking about two ints that are in a multi-column table that is making that many-to-many relationship. It's going to be unique, generally. If your application allows people to have the same job role multiple times, that would probably be a failure in business rules, and so generally multi-columns will be unique. And it's kind of ever-increasing, but not really, because the values within the multi-column, they're probably based on a couple ints, which may or may not be ever-increasing. And so let me show you this so you can kind of see this pattern. And so what I'm going to do, what I did here is I created an employee table. I also created a job role table. And then between the two, I created two job role tables. The first is two employee job role tables. The first one is using the identity column pattern, where we've got an identity column put on here, and that identity column is then used for the clustered index. In the second one, what I did is I still have that identity column, but instead of doing that as a clustered index, which it is clustered in the first, instead of doing it as a clustered index, I took the employee ID and the job role ID and made that the unique clustered index on the table. And so let's get these created. Actually, these are already created, and I've already filled them with data. What I did is I put in the cook, the butcher, and the candlestick maker, and then I just took some items from the employee table and threw them into this table. So let me show you some queries that go up against this. And so I've said already that that index selectivity matters, and there's a difference where there's a performance improvement that you get over this pattern compared to the identity column pattern because of the relationship between the records. And so let me turn on the execution plans and just run these two so you can see what we come back with. If we're just pulling back all of the candlestick makers, and these aren't really good employee names here. What I filled up the employee name table with was table names appended to schema names. And so they're not really table names. But let's take first a look at the performance between the two different patterns. So as I mentioned already, the first one with the ICP is the identity column pattern. This is the pattern that I most often see people end up using when they're choosing clustered indexes. So it's the one that I recommend that you start with. But it's not necessarily the one that you want to end with. And the reason why you don't want to end with it is that because you're looking up your rows based upon a value that has no meaning between the two multi-row joins, you're going to end up doing a lot more scans than you typically would. And so we're going to get 16 IOs against the employee table between the two tables. We're going to end up with 2 reads between the job role table. But if you look at between the multi-column join tables, you're seeing a lot more reads with the identity column pattern that you are with the multi-column pattern. And you want to take a look and watch for this, because in the execution plan is where you're going to see that big difference. Now these plans are a little bit big, and I'm going to try and make them mostly fit on the screen here. There we go. So I got them to mostly fit, and this is where the difference comes in between the plans. We've got an index seek on job role, we've got an index seek on job role identity column pattern, where we're joining these two together. We've got a key lookup to pull in additional values, and the reason why we got to pull in some additional values is because we can do the identity lookup, or we can do the index seek on the non-clustered index to get the people that match the job role names, but then when we go to get the employee IDs so that we can pull in from the employee ID and pull that information back up, we have to do an additional lookup. We have to do some additional work to get that information, because when we're going to this multi-column table, if you remember at the beginning I said what we want to do is focus on the direct access to the data. Well, because we're not sorting this by the direct path to the data, in this case the way that we go to this data is by job role, but we're sorting it by that unique value that identifies those two, that relationship. We've got to do extra work. Where if we were storing it by job role ID, we then can just go straight from job role ID, we pull out a job role, and then we go to employee and we do that match and we push the data back up. And that's where going by that foreign key pattern, the multi-column pattern can help you out. Now, and in some cases, it can make a big difference. In some cases, it can actually hinder you a little bit. Because as I mentioned, you have to focus on selectivity when you're looking at the multi-column pattern. In this case, the candlestick maker in the multi-column pattern is the value that we're using as the leading value. If we go back, we can take a look at that. Oh, actually, I was incorrect. Employee ID is the leading value. And so in some cases, there we go. In some cases, it can make a significant difference. So we just run those two and be in the right database. And so in this case, we're pulling out just purchasing and ship method between the two of them. And we're leading off of employee ID, and there are many more employees than there are job roles. And so if we take a look at the performance, we're going to find out that because we don't have the most selective value first, we actually don't see a really large difference in performance, even though we might see a difference if we're coming in from the other angle. And in this case, because we're coming in from a less than optimal path, we're seeing almost the exact same execution plan. So you do have to worry and work with the selectivity, and you want to make sure that the most selective values are first, and also the way in which you get to the data needs to be optimized. All right. Now the last pattern is using global unique identifiers. This is where people are typically using new ID or new sequential ID. We don't have a lot of time left because I do definitely want to answer a few questions before we finish up today. But this is basically the clustered index of last resort. It's completely non-related. It's like using an identity or a sequence value, but you're using the new ID or new sequential ID to create just a random collection of characters. And the idea generally when people are using this is that they've got a distributed application and they need to be able to assign values out in the field before they get pulled in. Maybe they're using merge replication or something like that. I'm not going to dig too deep into this. There are some cases where you do need to assign new identity and unique values throughout. And the biggest thing to remember when you're working with new ID and new sequential ID is that while these values will be static, because you're not going to change them, and while they will be unique, they are never narrow. And even though new sequential ID is called new sequential ID, it is not ever increasing. So I know a lot of people have switched from using new ID to using new sequential ID. Just be aware that new sequential ID gets reseeded whenever SQL Server service gets restarted. So it's sequential as long as you keep your SQL Server up and running forever. Once you restart your SQL Server, the seed gets reset and you can start to get out of order values that come back out, which then kills off your battle for ever increasing. The kicker is typically if you're using GUIDs or unique identifiers, the reason why you want to use them is because you've got distributed data, so you are stuck then with the new ID, and you aren't able to use the new sequential ID. Because if you use the new sequential ID on multiple different machines, well, they're not going to be sequential anyways, because they're only going to be sequential for that specific machine. And the one thing I just want to show when we're looking at global unique identifiers is I'm not going to go too much into using them except for I created a few tables that are using them, storing them as unique identifier, which is 16 bytes, or since they are 36 characters long, storing them as 36s. Be aware of how you are storing. If you do need to use sequentials, if you do need to use GUIDs, be aware of how you are storing them. I have seen a number of systems where people are storing them as varchar 36 because, well, that's what they look like. That is an extremely bad thing to do because you're going to be creating extremely large tables. Let's make sure I'm in the right database. Because if we just take a look at the difference between using an identity column and then using unique identifiers, we do see a significant increase in the number of pages that are required just for using the unique ID. Or if you store it as a string, you're doubling the amount of space that's required for the table. And so these are the things that you need to think about when you're choosing your clustered index. There's a lot of ways to do it, but I would generally start off with always adding a clustered index, making sure that when you're adding it that you're going for those goals of static, narrow, unique, and ever increasing. And start off with just using an identity column and clustering that, and then looking at your querying patterns to see, well, do I have a detailed relationship here? Do I have a many-to-many relationship here, where I can justify moving it to another set of columns? And just keep paying attention to that. And so just to summarize today, a lot of things is like clustered indexes are extremely important. Make sure that you look and keep them to the way that people are accessing the data, and continue to validate them over time, because you may find out that an application changes and now there's a better reason to go to a different set of columns for your clustered index. And just to plug a book that I worked on, I did work on a book that did focus specifically on indexing for the entire thing. These scripts actually came directly out of that book. If you are interested in learning more about indexing, this book that I did with Ted Kruger covers about pretty much everything that comes to indexing with SQL Server 2012. With that, I'm going to wrap up for today. Rachel, do we have any questions? I think we've got about 5 minutes before I need to end the session.
Perfect. Yeah, we actually do have a lot of questions. So I'm going to go ahead and just pick a few at random, and any that we don't get to, I'll pull the report and I'll send it to you, and you can follow up, like maybe in a blog or something.
Right.
Okay. First one is, are there any data types that you should avoid using?
Yes, unique identifier. Always avoid using that as much as possible. Go with int, and if int isn't enough values, go with big int. And if big int isn't enough values, then you're doing it wrong.
Good tip. All right, our next question is, for a multi-column index, does the order of the column matter? Can you use columns for different types for index?
The order of the columns do matter. I think I hopefully illustrated that enough on the example that I had. Based upon the two different patterns, the order in one case, there was a significant performance improvement, and in the other case, it was a much less, because it was actually, you got the identical plan.
Perfect.
And the data types do matter, as I've talked about, is when it comes to the size of the index.
All right. Let's see. Is the same performance if you? All right. I'm just going to read this one out loud because I'm not exactly sure what it means. But is it the same performance if you add include fields to the ICP index? Would you need to eliminate for key lookup, but it would still be more initial logistical reads?
Okay. So basically, when you're seeing key lookups, there's a few things that you can do, and one of the ways that you can remove key lookups is by adding in included columns. I didn't focus too much on that, or I didn't focus on that at all. And hopefully that motorcycle that just cruised by wasn't too loud. You can use included columns to get around some key lookup issues. The key is that if you're seeing a lot of key lookups and the key lookups appear to point to another column as being the more direct path to the data that you're going to on a routine basis, you'll often want to switch the clustered index. Instead of adding in more included columns, you may want to move the clustered index to those other columns. When it comes to the clustered index, you can't have included columns, and the reason why you can't have included columns is because that's where all the data is stored.
That makes sense to me.
All the points on that one.
All right, our next question is there a way to access your test code on foreign key and multi-column patterns to play with it more?
Oh, absolutely. It'll all be up on jasonstraight.com/go/indexing. Just look for this presentation name, and you should be able to click in and get that information. I will double check to make sure that this presentation is already up there. If not, I'll add it up later today.
Okay, great. Is the pattern mainly to pull less pages into the buffer cache?
that's mainly our goal. One of the main ways to improve performance, besides optimizing CPU utilization, is to optimize what you're using in memory. And if you can take, if you've got a 2 terabyte table and you've got half of it in memory and another third of it in memory because of a non-clustered index and a little bit more here and there between a few other indexes, if you could minimize that and keep everything to where it's in the path that you're most often accessing the data, you will improve performance by quite a bit.
All right, awesome. Thank you so much, Jason. That's all the time we have for questions, and thank you everyone for joining us. And be sure to join us for more free training on the T's every Tuesday and Thursday at 11 a.m. Eastern Time.